So our next speaker is Bernard Nienhuis from the Institute Lorenz Leiden, and he's going to be talking about nested paths in 2D percolation.
Thank you. It's quite a pleasure to be here. Thank you very much. I thank very much the organizers that they invited me here. It's just extremely pleasant to be here after all this period of non-traveling. The work I'll discuss was initiated in Paris when Jesper had invited me to spend a month there to finally write up some work I did with him many years ago. But in that month, so many new projects came up. I came away with more work than I got there. And so during this visit, it was mainly the thought, the idea of this. And we thought, who could possibly do what we have invented? And then we thought of Yaojing Deng, who is very good in numerics. And he started working with us, and he, in the process, collected a lot of his students to work with us. And I mention here only one because the others mainly left physics. I always want to know exactly what the words mean that I speak about. So I decided to look up percolation. And of course, it's a Latin word originally. So I thought, what does it really mean? And well, the noun means filtering. That makes sense. And then the verb, the infinitive. Well, it's translated by Google Translate. This is really an exercise in Google Translate. It's translated in a filter. That makes sense. So I thought, let me look at the verb forms. First person singular. I filter. Well, that means color, according to Google Translate. Well, there's a native Latin speaker here. Anyway, the second person singular wasn't. He was unable to translate. He just left it as it was. So I put a question mark. The third is filter. Well, that remains the same. But then, interesting. The first person plural means honor, and actually it said to honor, so it turns it into a. And then finally, the second and third personal plural, well, they make relative sense. So filtering is really what is left over. I thought, excuse me. Oh, you mean in Google Translate it is missing, or what?
Most probably, I will check, but it could be that the first person of I percolate, it's difficult to percolate.
Okay, it could be. Yeah. I think you may be true, but I think you think too highly of Google Translate. Anyway. So it's really not language, it's all visual. So this is really what's percolation. As you all know, when we think of percolation, we think of some mixture of open and closed material. Say the yellow is sand in sandstone, the blue is water, and the question is the sandstone permeable or not for water? And well, this is really all I have to say. Any questions? Let's look at it from a middle closer up. The question here, you can easily see here the water can go through from left to right and from top to bottom. And it is sometimes more interesting not to look at the material, the matter, but to look at the boundaries between the different types of material. And so you can look only at those material, and really the information is all there, except you have to decide now which is yellow and which is blue. But that's just a 2-to-1 correspondence. And now in words, percolation is really the question of permeability of some material depending on the microscopic porosity. And we usually think of a random mixture of open and closed material. If you think of coffee, you have coffee grinds, and they're packed together in this espresso machine, and when the holes are big enough, the water can go through. You make concrete, and if you're a poor builder, then you have too little sand and too little cement in your things, and your slabs of concrete may be leaking. And everything has some sort of microscopic scale, the grinds of the coffee and the pores in the concrete. And we've learned that that the interaction between these different parts of material are irrelevant. So in models, we completely do without interactions. And what we're really interested in is the sharp transition between a permeable and a non-permeable phase. The transition is sharp, but it's a continuous transition, and it's actually a transition in any dimension. It's classical for dimensions larger than 6. And in this talk, I will focus on point operators in the percolating system at the phase transition. I will look particularly at critical exponents of conformal weights of these operators. And I'll start with looking back at some known families of operators that have been studied over the years. And I will then introduce, and that's the main topic of this talk, a new family that turns out to be indeed a useful member. So here is a picture where I have dropped out 2 hexagons in the slab, and those they represent the positions of the insertion of point operators. And in this case, I'm interested in operators that look at the domain walls between the open and the closed material. And in this case, these 2-point function, it measures the probability that the 2 points are connected by a given number of domain walls. In this picture, it's 2. And as you well know, these functions typically in an infinite plane decay as a power of the distance with an exponent which I here call xwm. I'll explain later. And in fact, I typically I often look more at the 1-point function, and then I do not look at an infinite plane. I have a finite disk domain with a center where I insert the operator, and I look at the number of domain walls that connect the center to the boundary. And then you can find power law behavior with respect to the size, the radius of the disk. In this case, you see that there are 4 domain walls connecting the center of the disk with a boundary. And it's natural to think that n should always be an even number because the domain walls are they're on the domain. They're yellow blue or blue yellow, and you need an equal number of each. But since there is a symmetry between the yellow and the blue hexagons, I can actually insert an anti-cyclic center. So if I go around once, then I flip yellow to blue on the, say, the positive real axis. And then you can see you have 3 domain walls. The different colors are only there to make them distinguishable for the eye. They're not particularly. Could you say it again?
Sorry, I was just asking about terminology. So n can only be 0, 2, 4, or 6 in your example, or n can be arbitrarily large?
N can be any number. Oh,
but
yeah, in this, when the little hole in the center is a single hexagon, it cannot be bigger than 6.
Okay.
But I can make this hole a little bigger, and then I can allow more domain walls.
Okay, and is that the same point for the 2-point function that you showed earlier?
That's true.
Okay, thanks.
Yeah. So when I say point operators, by point I mean point only on the scale of the macroscopic scale. In fact, now I come to the name of this exponent. It's called, it's known as the watermelon exponent. I think it's introduced by Duplantier and Saleur. And they invented this name because of the picture. If you have this cartoon of the diagrams of the 2-point function, then it looks a bit like a melon. And here we're not so interested in the name, but more in the value of the exponent. And it has this, simple form, n squared minus 1 over 12. And now I'll go and introduce another operator that deals with domain walls, but not domain walls starting at the insertion point of the operators, but domain walls that surround it. So in this case, I have again a disk, and the center, I put the operator, and I simply count the number of domain walls that surround that point. And in this picture, there are 3 such domain walls. I again can find power law behavior with the distance, with the radius of the disk, but not for a fixed number of domain walls, but for the generating function of the probability distribution of n domain walls. And so now the power law dependence is the power law function, the exponent does not depend on the number of domain walls. It depends on some weight, z, which is effectively the weight of the domain walls that surround the center. And I call it, I'll label it NL for nested loops. And the 2-point function, again, I can picture. And here, of course, in the domain walls here are colored again to make them visible. I count only in this generating function, I count only the domain walls that separate the 2 points. So the domain walls that surround either one or the other of the 2 points, but not the domain walls that surround both. And so you could think of a similar kitchen name for the exponent, like instead of watermelon exponent, I now have an open oyster exponent from this cartoon, but we decided on nested loops. And the exponent again is a known exponent. It's been from a number of sources, it's been calculated for originally maybe 30 years ago or so. You see the 1/12 again, but now it is preceded by 3/4 of phi squared, where phi is the argument of a cosine, which is labeled, which is given to give a value, parameterize the weight of the loops. Now, some special cases, if I give the weight, if I use the weight 1, then of course I do nothing. So the exponent should be 0, which is indeed correct. If I decide that I give the weight 0 to these loops, so I forbid all domain walls surrounding the operator insertion points, then the exponent can be calculated, and it's 548 from that same formula. And when you think, yes? Oh, you're right. Yeah, there is that's an accident. That's there should not be a pi here. Yeah, this is phi is 1/3 or 1/2, not pi or 3 or pi or. I have a little bit too abundant with the pi's. Now, if there are no domain walls surrounding a insertion point, then you know that there must be a path over either open or closed hexagons. So the choice of setting z to be equal to 0 forces the existence of at least one path between the insertion points or from between the insertion point and the boundary in these correlation functions. So that brings you to the idea of counting paths rather than domain walls. And by a path, I always mean a sequence of steps over the hexagons, or over the either open or the closed hexagons. And in all cases, hexagons of the same color. In this example here, you can see that the origin has both a yellow and a blue border, and the blue is connected to the boundary. So there are blue paths from the origin to the boundary. There are many different paths are possible, but you can only make 2 simultaneous, which are non-overlapping. If you want to make more than 2, then they will share a hexagon. So in this case, I will count these paths as 2. And that again gives you a power law behavior. There is this probability function. The probability that there are at least n paths from the origin to the boundary is called the monochromatic arm exponent. Monochromatic simply from the fact that you want the paths to be all of the same color. And it's been studied for a long time. It was originally the case of two paths, was called the backbone exponent, from its relation to say stripping a percolation cluster from all its dangling parts that are singly connected to the cluster. So you retain in the cluster only those hexagons which are doubly connected to each other, and that was called the backbone. But that is really equivalent to having two paths from every point in the cluster to every other point. And unfortunately, this exponent is not known, but there is in fact a conjecture which is not published. It is by Befferin and Nolin. It's already, what is it, 13 years old. They gave me permission to mention it. It's not on archive, but I do have a preprint. And you see here the relation. So these are numerical data, but also obtained by the same authors. And you see that it agrees pretty well with this conjecture. Unfortunately, it doesn't agree with the best estimates of this backbone exponent. But the differences are so small that you might suspect these best estimates. So I personally favor this nice formula, but if anybody is interested in discussing it, I would I have no idea how to prove it. I've been thinking about it for many days and nights. Yes. You mean for NS2? So these are numerical data. So these data are obtained by Befferin and Nolin by simulation. Completely different, yeah. So these are, this is a transfer matrix. I actually forget the method that they used, but so I mean it's clear that the error bars exclude this number, but it's not so clear whether you should believe the error bars. But, I mean, they're definitely competent researchers, but with these simulations, it's difficult to be sure. Say that again. It's hard to make what? Yeah, it means easy to simulate, but to get a good sample to get good statistics. Of course, it's much easier to simulate than interacting models. That's clear. I agree. No, I mean, that is, I mean, if I mean, let's not discuss the virtues of these authors, but I sort now I use the word monochromatic to emphasize the fact that the different arms are all of the same color. In all cases, by paths, I mean that the steps in the path are, of course, of the same color. I mean, otherwise the steps are just a random walk. But you could imagine that you allow paths, some over open and others over closed hexagons. And you could relax the monochromatic restriction. And of course, relaxing a restriction can only increase probability. So you can only decrease exponents. The exponent was always with a negative, with a minus in front. And so and in fact, it is known that the bichromatic arm exponent, it's often called polychromatic arm exponent, but I find poly a little bit overdone for two colors. And that is equal to the watermelon exponent. I'll have a few more words on that, but I won't digress too much. And it's a little counterintuitive to me, at least, that the probability of having different arms of different color, that probability is larger, strictly larger than the probability that you have multiple arms of the same color. There's no interaction, so why do these arms influence each other? You can think of, suppose I have 6 blue arms from the center, and then I wonder about the possibility of having an additional yellow arm, and that is known to be of an asymptotically zero probability, because it is known that the monochromatic arm exponent of n arms is less than the watermelon exponent or the polychromatic arm exponent of 1 more arms. And that is actually rigorously proven, again by Beffera. Should I speak slow?
No, you are muted.
Close it? Did you hear that? Aha, I shouldn't be too close to this. I took that position to be able to keep an eye on the clock. Yeah, okay. So the statement that these two exponents, the bichromatic arm exponent of n arms and the watermelon exponent of n domain walls, are the same. Is it? It's muted. Oh, you want to close it? Oh, here. Oh, that's it. Okay, thanks. The proof that these two exponents are the same is claimed by Eitzenman, Duplantier, and Aharoni. And when you read the paper, it's very difficult to discover that proof. And for us, it was, I mean, we really wanted to understand this because we wanted to apply the technique to other things. So we asked Eitzelman and Duplantier to explain us the proof, but they couldn't. Well, eventually we worked hard on it and we wrote down the proof, but it's okay. We'll probably put it in some paper. I guess the authors did prove this, but didn't write it down well enough to be able to read it themselves. I didn't ask Aaroni. I should, yeah. Yeah, Duplantier was around. I was in Paris, and Eitzelman I communicated with by email. I don't know why I didn't ask Aaroni, but maybe. So since we have these two types of operators related to domain walls, namely the watermelon and the nested loops, can't we do the same thing for paths? We can have paths being initiated at the insertion point of an operator, but we can also have paths surrounding the insertion point of an operator. And so this is what we studied. And this is just I changed colors, but that's not significant. Not a political choice or anything. So here I also, the shape that I take a hexagon or a disk, that doesn't really matter too much. I have a domain and I put somewhere near the middle a point, and I count the number of paths that I can possibly make on, say, red faces here that do not have any hexagons in common. And I take the convention that all these paths are part of the same cluster. That's really, it's not, I'm not sure this is essential, but this is a convention we chose. It is effectively guided by our experience on the monochromatic path exponents, monochromatic path events, that there you could say statistically they must all be part of the same cluster when the system is big enough. Here it's not so easy to take that argument, but we just enforced it to just make things well defined. And if they're all part of the same cluster, and then that cluster must also connect the center to the outside world, to the boundary. We are interested in getting the exponent of this operator, and of course we want to know if it's universal. So we looked at another prototypical percolation model, bond percolation on the square lattice. And here's another example of a configuration. Here there is another choice that you have to make. If you take bond percolation, when do you consider paths non-overlapping? They obviously should not share a bond, an edge, but they may share a site. And that's what we decided to allow. I don't think this is essential, but you have to do the statistics properly, you have to make a consistent choice somewhere. And we measured the exponents simply by simulating and on systems, as you mean, the capital L here is the diagonal, or the diagonal of the hexagon. of the square. And you can see here that you get something that looks reasonably well as a power law. The drawn lines, unfortunately, are not straight lines; they're connecting lines. But the ones that, so here, the ones on top are negative exponents, meaning that the weight of the diagrams increase with the size. When the exponents become very positive, then you see that they're slightly more curved. The statistics is not as good. And that's also, these are negative weights, in fact. And that means that you get cancellations. So the statistics becomes a lot worse in these cases, more difficult to get the reliable data. And here we plot the exponent for the two models, the square bond percolation and this triangular side percolation. And you can see that they agree very well. And I plot them in analogy with the nested loop exponent against phi squared, where phi is given again by the parameterization of the weight z. I think we did some stronger test of universality by allowing many other models, and they are still within the even the points, they're pretty close. So universality is definitely satisfied. And here you can also see that where the data becomes weaker, there's also strong dependence on, there's something funny happening here. There is the drawn line is, I'll come to that in a moment. We tried, in fact, to guess what is this function, this nested path exponent as a function of z or as a function of phi, if you like. What does it look like? So let's first list the things that we already know. When z is 0, so that means we do not allow any path surrounding the origin, but we still have demanded the fact that the origin is connected to the boundary by an open path. And we, at the same time, we claim that there is no path surrounding the origin. That means it must be the case that there's not only an open path from the origin to the outside world, but also a closed path. So it's equal to the watermelon exponent with 2 domain walls. So that exponent should be a quarter. When z is 1, that means we don't even do anything with the paths. We simply ignore them. But we still have this constraint that we demand a path from the origin to the boundary. So that is equal to the just the magnetic Potts percolation exponent of 548. So these are the 2 of the things that we know beforehand, and then we make some observations in the data. First, there is a strong indication of a slope of 3/4, the same 3/4 slope that we would see in the nested loop exponent. when the weight is equal to 2, that means phi is equal to 0. If you look at the, go back to, you see it's very strong indication that that should be 0. It's hard to believe that it's a very small number other than 0. So this was at this point just an observation, and then there is something funny happening at a weight of z a little bit less than -1, perhaps a pole. So we proposed this form, and that form takes care of some of the observations that some of the facts that we know and some of the observations. And this has 2 free parameters. This table is effectively the list of observations and known facts from the previous slide. And so we adjusted the parameter A and B so that we make it consistent with all our knowledge or observations. And the answer is this. And so this is a conjecture at this point. Pardon? Oh yeah, no, but some of the things are taken care of. So this is this slope. That's the 3/4 slope. They've already stuck in. And the 0, when z is 2 or phi is 0, that is, so I made this. Yeah. Yeah, so the number of parameters are only the first 2 lines. Those are not yet and it's relatively attractive expression. I mean, the numbers make sense. The 548 is a well-known number in percolation. The 3/4 we knew. The numerics is really excellent. I mean, I think I have it here again. So the drawn line is the formula. And so that's really quite excellent numerics. However, this pole at 2/3 value of phi squared. So this phi is a phase up to a factor pi, and then phi is then the square root of 2/3. That's a very strange position for such a dramatic thing like a. So okay, we give it as a conjecture, but we won't really put our faith in it. We give our let's see, what else do I want to say? Oh yeah, what is the time? Is time up really, or? Okay, so the this is worth going through. Something funny happens. I mean, this observation that the weight, when the weight is z is 2, that the exponent is 0. That is comes out of nowhere. But here you see the data. This is this W of 2 for side percolation, and this is not this is the complete probability. And so that really is definitely consistent with exponent 0. But it's even consistent with amplitude exactly 1. On the square lattice, it's not as nice, but still consistent with 0 exponent. And we also noted that these first three, all up to diagonal 7, for the hexagon, the data, it is exactly 1. So you could do the complete partition sum and find that it's exactly 1. So it looks like something that can be proven. And I'll go through the proof quickly, and then I'll let you go. First, let's consider any configuration in side percolation on the triangular lattice, or the configuration of the hexagons. So here's a configuration. And then I consider a maximal set of bichromatic paths. So the paths themselves are single colored, but the different paths could be different colors. And they nest each other, and they form a nest around the origin. And I draw them as close to the origin as possible, given the ones that are inside. So say this is the closest, the path closest to the origin as possible, and then given this one, then this green one is the next, and then there is another one. So this is red, green, red coloring. Now, I define an operator, Pn, which flips the colors of all the hexagons on the nth path and everything inside. So with 3 paths, I have 3 such operators. And then, so you can see here, this is flipping, this is P2. I flip the color of these two, of everything inside the second path, including the second path itself. And then I consider the collection of 2 to the L configurations generated by these operators. And of all those open paths, of all those configurations, only one has all paths open, all paths red. And those contribute to my correlation function. But of course, that is equal to all the configurations together. And this is this argument I can follow for any arbitrary configuration. So this proves that indeed this weight is equal to 1. And I think that is what brings me to the close. So what have I done? I have gone with you through a number of well-known point operators in percolation, and I've introduced a new one. I have proposed for you a value of the exponent with some reservation of my faith in it. I've shown you a proof that at least this exponent is 0 when the weight is 2. And I've also shown you a conjecture by Beffara and Nolin, which I find at least as interesting as our own conjecture. And so this is what I've told you, and this is just a few remarks of things that are still going on now. We from the say the functionality from the weight of the weight, say W sub Z, the generating function, you can derive some statistics of having L loops. And what is the probability of having L loops? How does that depend on the size of the system, etc.? And that can actually be, you can find nice expressions for that. And those expressions we also tested against the simulations. And we made some progress generalizing all this to Potts models or models where the weight of the other loops are also given are different from one. Thank you very much.
Thank you. Any questions?
If, as I suppose, you first did your numerical simulation and then investigated and found these beautiful proofs at the end, the proof induces now a much faster method of making numerical simulations. You make a whatever percolation configuration, you apply your iteration so that you have probability 1 of having your stuff connecting to the boundary, don't have rejections, and you have a point for the z/2 value. So now you don't have that you make percolation. If it doesn't have the gigantic cluster that dashes the boundary, you don't have a point. You have huge statistics. Was I clear? I mean, if you just did
not to me. I mean, I have difficulty understanding all the words you say. So I take about 2 out of every 3 words I understand.
I will say that in a proper English now. If you do just the numerical simulation of your definition, you make a random percolation cluster.
Yeah.
If all the surrounding paths are in the same percolation cluster, you put it in your histogram. Otherwise, you throw it away.
Yes.
Now, the proof that you showed us induces us a better algorithm. Every configuration count, just with the power 2 to the minus L. The statistics is much better. It will be much faster, and you will have much beautiful points. No, this was not proper English. Okay.
There you.
It is the measure reweighted by 2 to the minus L. So it is the measure in z/2. That's the point of the proof.
Yeah.
So I keep.
Yeah. So I mean, okay. So you're proposing, I mean, using the proof to make a better statistics. Yeah, I'll think about it. Sounds plausible.
Yeah, so what is your take on analytical perspectives on any of these exponents? Because so as far as I know, the reason why the backbone is still not known is because there is no connection to Coulomb gas type of calculations. And I mean, here this seems even wilder. So I mean, is there a hope that some other method will ever give analytical results? Or,
Okay, I have the intuition that this conjecture by Beffera and Nolin can be proven. Not so much by when, but it's an intuition. So what does it mean? But I don't see any way like Coulomb gas or conformal field theory or SLE, and our new conjecture is even more hopeless. So I think I said what you expected me to say.
But is there something else?
Is there something else?
Apart from, yeah, something different from Coulomb gas, CFT and SLE, is there?
Are there other methods?
Yes. Yes. is there a hope? that
Hopefully, maybe 2 years from now. I have no idea, but
Okay.
Yet another beautiful consequence of your proof is that you have also the exponents for the statistics in which the surrounding loops have alternating colors. The two of them are related. You can define now an X AP for alternating nested paths in which you count Z to the number of green, red, green, red, green, red.
Yeah.
But
Yeah,
that's
I
again
think
just the counting of the
I think
images.
the alternation is not necessary. I mean, as soon as you have more, if you have paths of different colors, I believe you can. I mean, you can prove. Well, I'm not. Yeah. Maybe I'm.
This one requires a blackboard.
Yeah, it does.
Who else? Continue, Pasi.
Anyone else? Okay, if not, thanks again.